What we've looked at in the last two examples are two infinite series. So these are infinite and they both converge. This being a geometric series, and this is a different type of series, and this one happens to converge. And if the terms are going to zero, it has a possibility of converging. So we're going to look at some other series, and some of them don't converge because although some series go to zero, they don't go to zero fast enough, so they diverge. Now, one thing to note, and make a note of this please, geometric series, infinite geometric series where the r is less than 1 always converge. Okay, they will always have a finite sum because the denominator is exponential, and that means that the denominator is getting big enough, fast enough for the series to converge. This power 2 function on the bottom in the denominator, this is being squared in the denominator. This one happens to get small enough, fast enough for it to converge. So the denominator is strong enough for this to converge. There are some series that do not converge. So a harmonic series is an example. And a harmonic series is an interesting series, and this is called a harmonic series because these ratios tend to form natural harmonics for music. This series basically is just going to be 1 divided by 1, 1 divided by 2. So as we increase the number of terms, we're just going to divide, the n is just going to get bigger. And the limit as Tn goes to infinity, for Tn, or we'll just write this as 1 over n. This is what the sequence looks like. This is definitely going to 0, so it meets the first criteria. However, this series, this infinite series, diverges. Okay, it has an infinite sum, although, so s equals infinity. Now, although each term's getting smaller, eventually we're adding 0. These terms are not getting small enough, fast enough to kind of battle the idea that we're adding an infinite number of things. So this is what we call divergent. If we take a look at and compare a geometric series in blue, so this is a geometric series, so the blue bars and the blue line represent the geometric series. This is an exponential function. Okay, so each term, when we take this term of 0.5, 1/4, 1/8, and add those up, if you look at the progression of this, notice that the exponential function goes to 0 very, very quickly. And so these sums get very small very quickly. And so when we add up the blue bars, we're going to have a finite sum. It ends up equaling 1. If we compare this to the 1 over x function, so 1 over 2, 1 over 3, 1 over 4, if we look at that function, it is a 1 over x function, and it does not go to 0 very quickly. It stays well above 0 for a long, long time. It will eventually go to 0, but not anything like the exponential function. So what ends up happening is, although we're going to 0, because we're adding an infinite number of things that are not getting to 0 fast enough, this sum becomes infinite. So 1 over n become the sum of 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 all the way to 1 over infinity. That sum ends up having an infinite sum. And there's going to be, you can see why that happens when we look at the proof videos for that.